Hey, there we are, having some slight technical difficulties. All right, so today we're going to be writing the GAT-C processor emulator, and the GAT-C processor emulator is based off of this offhand comment that Tetsu made in the C group, C and Assembler group on X, formerly Twitter, about C probably being God's favorite language, programming language, and I said, well, it's GAT-C, right? GATC, DNA, all that thing. So I asked AI to go ahead and make me some image of God, sorta. Looks more like a modern Jesus, sitting in front of a computer and spewing DNA, and that's kind of a DNA tree there behind him, and all the various animals. Anyway, nice and psychedelic. Kind of gets the idea across. Good enough for free AI, right? So anyway, let's get into it. We'll get into the main screen here. And the first thing we want to bring up is our instruction set. So, GAT-C God's assembly text code, why not? It's a processor. The assembly instructions are based off the letters of DNA, and so I started looking at it. They're in the order of GATC. I don't know why that is. Maybe that was the order they were found first. But it also happens to be the order of their molecular weight, from largest to smallest. And conveniently, this least significant digit here of each one actually gives us the order that we're going to use the letters as substitutes for numbers. So we now have a base 4 numbering system, as if things weren't confusing enough. So C equals 0, T equals 1, A equals 2, G equals 3. But conveniently, 4 characters in a base 4 numbering set gives us 0 to 255 like a single byte. So instead of having 2 characters in hexadecimal or 2 to 3 characters in decimal, we have 4 characters, up to 4 characters anyway, to fully represent a byte's worth of data. And then we go ahead and assign some command formats. So the basic command format is going to be 4 letters long. First is the command letter, G, A, T, and C, then an operational letter, and then 2 letters for a register. And it's base 4, so 2 letters gives us 0 to 15, convenient for registers, right? And then after that, we'll have 4 or more digits or characters to represent a memory address. So what this means is that with this scheme, you can be little or big Indian, you can be 8-byte, although that would be kind of a waste, or 8-bit rather, 16-bit, 32-bit, 64-bit, it all depends on how much memory you want to write here for the commands. So it could be just about any size. I'm going to go with 16-bit and big Indian so that it's easy to take the letters out of a string and convert them to a number. Obviously, internally, it's on x86, so it's going to be little Indian internally. But in any case, so occasionally there's an X character, and that X character means it doesn't matter. There's only a couple of places where that exists. But they must be filled with something. Maybe we may fill them with random values, and we call that junk DNA, right? Sure, that sounds like a way to go. So the registers in the memory layout, so this is going to be a reduced instruction set machine. Very few instructions relative to a complex instruction set machine, like where you had separate instructions for talking to registers versus memory and I/O ports. In this case, what we do is we have the register numbers are actually just aliases for the first 16 memory locations. Not exactly the first 16 memory locations, because it's the first 16 word size. So in our case, we pick 16 bits. So the first 16 16-bit locations. So the first 32 bytes of memory are going to be dedicated to the registers in our version. Obviously, they'd be bigger if you picked a bigger memory size. So, but by doing that, we can read to and from memory, from a register to memory, or from memory to a register, just by using this sort of alias name for the registers. And otherwise, it just makes things pretty straightforward. Now, we're going to be doing a lot of zeros, right? Because of the memory size. So I think in the assembler, which we've yet to write, we'll use certain special characters to take the place of these larger characters. So in the cases where we are, well, we seem to be dropping a lot of frames here. Only using 5% of the CPU though. Huh. Wonder why that is. Anyway, if there's any what do you call? If you see any kind of problems, let me know. Now we're claiming to have excellent stuff. Streaming quite well. Well, turns out that was probably too many kilobits per second. Well, we'll take a look back at this later and see if we've got to change it. But right now, it seems better all around. All right. Continuing on. Because our assembler is going to have a lot of zeros or a lot of C's in a number of cases, we wanted to create sort of an abbreviation. It's also sort of like compression, if you will. Anytime we see a collection of a whole set of 8 zeros, we replace it with a tilde, 4 zeros with a star, 2 zeros with an underscore, and it should make writing the code a lot easier. So that's the plan on that. Got a fly buzzing around my head. Anyway, so I think the assembler is probably going to go ahead and use the same, what did I call them here? Directive letters for setting the original address and things like that. All white space will be ignored, and we can use ASCII, 8-bit or Unicode, 16-bit character codes in the data that we're using because we have a 16-bit machine now. So, first command, the G's for Go, basically flow control. So it changes the PC to the memory address if the register value matches the operation. So for example, if we say G, G, and register 1, that would be jump if register 1 is 0. And if you say GA, it would be GA0 T for register 1, 0 T here for register 1. So if we say GATC GATC itself would actually be interpreted as jump to this memory location if register 1 is not 0 or anything other than 0. So 0, not 0, a jump on the carry or borrow bit being set. We'll get into the ALU here next. Or it will be a function call. So GC register and function call. And as we have a number of these examples shown down here, so GC00 or XX doesn't matter because it's always going to make the call regardless of the status of the register. And I tried thinking of doing something with that number, you know. Maybe automatically giving it some stack space, I don't know. But really it's just going to call the function. So that's going to consist of storing the program counter into the stack pointer, increasing the stack pointer by 2. Actually, I guess that's a -2 because stack pointer grows down just like the stack grows up. And then the program counter is going to equal whatever memory address you gave it. So that's the basics of the Go command. conditional jumps in 0, not 0, and the carry bits, or a function call. Then we have the ALU command. ALU command, conveniently A, right? So we have different modes of arithmetic and logic units. And so we have basically 2 4-character instructions that make up 1. So we're going to say we're going to use the ALU. We want the operation mode to either be powers, arithmetic, bitwise, or shift in urinary functions. So, and then the RR will be the register. So all of the ALU is done register to register. So, for example, AATC would be arithmetic. First letter, come on now. First letter is arithmetic. The next one is arithmetic. First one is ALU. The next letter is arithmetic. And arithmetic then has GATC of plus, minus, multiply, divide. So the T then says that we are, I might have that wrong. Yeah, I think I have these instructions wrong. I originally wrote them with a different scheme in mind. But the new scheme would be G, or A for the ALU. An operation mode of A would give us the mathematics functions, and then a register would be TC for register 1, or the A register, and TT would be register 2. I should come up with a way I could type these out here. So let's just put this down here. So say, for example, we had A for ALU, A for arithmetic functionality of the ALU, and then G for plus, and then a register number. A register number of CT is 0, 1. Register 0 is going to be the 0 register. So it's always hard-coded at 0, but we'll get to the registers later. And then the next part of this would be A for continuing an ALU command. Then the might be able to salvage that letter and use it for something else. But right now, we'll go with this. So ALU, arithmetic, plus register. These are destination register of 1. ALU, operation, and this operation for plus would be G, so AG, and the destination register of GA, or CA, which is 0, 2. So this says use the ALU arithmetic functions to add the contents of this register, register 2, to the contents of register 1. I have an extra A in all this. There we go. No, wait. AA. Yeah. AA. CT. There we go. So our destination register is CT, our source register is CA, and it's basically A equals A plus B. So we'll get into that a little bit more, but that's the general plan that we're going with. Really need to change these examples. So moving on, though, we have T for transfer command, which is to transfer memory from the registers to someplace in memory, or from someplace in memory back to the registers. And we have 2 modes of this. which is either that we're moving a single byte, the least significant byte, or we're moving the number of bits in your register. So in our case, it'd be 2 bytes or 16 bits. And that would be transferred to and from register to memory. And, you know, again, this, I kind of debated about whether this would be a singular command or a double command. I kind of like that it's a singular command, but if it were a double command, we'd be able to fit a little bit more in there. Really, the goal is to be able to get away with most of it being 12 character instructions. The actual 4 characters for the main instruction, and then 8 characters, or up to 8 characters for the address. And of course, once you feed it into the processor, you need to put in all those C's for 0, leading zeros, or leading C's, I guess. So in other words, here 2 bytes starting at this location, moved into register A, use transfer register to memory. Well, I got these examples all messed up. T and then G should be register to memory, not memory to register. Oh, what a mess. Well, I'm going to have to change those around. But luckily, this is not exactly, I'm not going to be going off of these examples. But that's basically the transfer commands. I'm going to go off of this, not the examples. I have to remind myself that I've screwed up the examples. It's kind of like, don't read the comments, read the code, right? So, then we get to the C's. And the C's are all about the number of, or rather, the C is the controls. In other words, in this case, it's the return functions. We can either return from a regular function using the G command, or we can return from an interrupt. So we also have interrupts in here. And then because I had the letters left over that I didn't know what to do with, I thought perhaps we'll include dereferencing. So we can say register equals the dereference of this memory, or the register equals the dereference of the memory plus the current contents of the register. And that's just convenient for index or array indexing and the like. So, like I said, I should probably go back in and change these examples and match them up. But for now, we'll move on. Let's. I guess I should also have probably spoken about the registers earlier in the in this. We'll get this rearranged. But the registers 0 through 15. The 0 register is a read-only fixed at 0. It would be asterisk asterisk. For all 8. Did I guess it could have just been tilde too. I really should have been editing the document while I was talking. Anyway, the idea being that I could just write in tilde, and that means all 0. All balls, as we used to say. Then we have the A, B, C, D, E, F registers, all general purpose registers. Then we have our input registers of A, B, and C, and our output registers of A, B, and C. Then we have your program register, your stack pointer, and your flags registers. So the flag registers contain a number of flags for both the C and B flags, the carry and borrow flags from the ALU, but also whether there's a hardware interrupt, or there's an interrupt or new data on the input ports of A, B, and C, or we have the interrupts masked, or we have a software interrupt. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, there we go. And the idea is that those would all be either C or T, meaning 0 or 1, or possibly they could be C or anything other than C. Which, in any case, where we got carry, borrow, hardware interrupt, interrupts for inputs, interrupt mask, and software interrupt. And no bracket here either. Ooh, that's interesting. And of course the C and the B are read-only because they're outputs of the ALU commands. But the other ones could be written to. We write to this register and set the 0th bit or 0th character to something other than C for 0. Set it to something else, and then you get a essentially you've fired off a software interrupt. So the idea is that, you know, hardware interrupt for generic use, and then input interrupts for the input values. And then set or clear. So to clear interrupts, you just delete these values from that register. So you're just transferring from the 0 register into that, or, and I've kind of debated going back and forth on this, perhaps we get rid of the F register, have A through E, and have a 1 register, because so far we have no immediate mode, so we can't load an immediate value into a register. So perhaps we need a 1 value, or, as what I was also thinking, is we would have a well, the assembler would put the immediate values that you typically use, and it would just put those in a memory location, and then we could read those values from a memory location. Anyway, long story short, that's the general plan. So the first thing we're actually going to do is set up memory and the registers. And to do that, we already have our Visual Studio up and running over here. And so let's go ahead and start. What do we need? We need our registers. So let's get our register plan here. And to make this straightforward, because the registers are aliases for the memory locations, we're going to start off with memory. And we're just going to define it as global to the program. So we're going to have a bunch of characters, memory, and 535 of them. And then we're going to have our registers, but our registers are going to be a data structure. So type def struct regs, and does it really need to be that? I don't think it needs to be that. Because quite frankly, all our registers is unsigned short, pointer, regs, yeah, unsigned short pointer regs, and we've got 16 of them. And they are going to equal, well, they're not actually unsigned short pointers. How best to do this? Because really what they're going to be is pointers into this memory block. So, yeah, I guess they are unsigned short pointers. Registers, we got 16 of them. It's going to equal memory to the 0. But since it's a pointer, we're going to take the address of that. And then we're going to have, I might have to cast all those too. That's going to be something of a pain. That'll be kind of ugly. Unsigned short pointer cast. Yeah, might as well. 0, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5, 6, 7, 8, 12, 13, 14, 15. I got some extras. 15. All right, so that's memory address 2. $14, 16, 18, 20, 22, 24, 26, and 28. Does that look right? Yeah, every other byte. So each register is 0, 1, 2, 3, 4, 5, etc. And 28, 29. So that way we can index our registers pointer, dereference them easy enough. They overlap memory as planned. Let's see. It's pretty much what our plan was for the first 15. Although that doesn't seem like the first 15 if I only get to 28, right? How am I 1 or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There we go. 28, 29. Yeah. 30 and 31. That's our 16 bytes. All right, that's all of those. Let's see, we might want to make an alias for these names. So how do we want to make an alias for the names? What do you think? Make an enum, maybe? Yeah, let's do the enum. Why not? Let's see. Enum. Reg names. We got the 0. Let's make them all lowercase. Sorry. 0 register. A. That's not A reg. B reg. C reg. A reg. And F reg. We'll just call this the Z reg. Those are the first of them. Then what do we got? We got input A, B, and C, output A, B, and C. So I IA for input A. We know these are registers, so it's kind of redundant using the reg in there. And most of the time, the emulation is just going to go off the number. So, but other things that we might do, we'll want to use them by name. So input A, input B, input C, B, output A, output B, output C. Now we get into the special purpose registers, PC, SP, and flags. We'll capitalize those. Should we capitalize them? I don't know. Let's keep with the theme, shall we? There we go. So again, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There we go. That way, if I primarily reference the program counter and the stack pointer in the code, also the flags register, I can basically do this kind of number with regs to the FL, da 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 da, da, right? So I think that's pretty much the setup that we've got for memory. And for now, we're going to want to, well, we're going to want to have a process function for each of the categories, right? And let's see. Let's just prototype those functions here. We'll call it process go commands. And the process go command is going to take a pointer to the car pointer to the input. And since we're just prototyping for now, process transfer, process ALU, and process CTRL. And then we're just going to pass the number or the rest of the input to each function. And we're probably going to have a return code. What are we going to have? Perhaps an int, which will be how many characters to progress by. Perhaps. They're always going to progress by the same amount, actually. So, well, let's just do character pointer output to where, you know, the next character to process. So we can just, you know, have a pointer character to where we are in the program and make it equal to each one as we process. There we go. Now, let's see. Our original plan was to have bytes 32 through 43 be the interrupt service routines. So we can probably treat those as registers, even though they're outside the range of the first 15 registers. So let's go ahead and add those back, or add those up here. How many is it? 1, 2, 3, 4, 5, 6 more. There we go. A comma there. 32 over 36, 38, 40, and 42. Right, 42 and 43 are the reset PC. So these are the ISRs. So let's go ahead and name them here in the enum. I already used I for input. We can call them ISR. A, R, B, SRC, ISR hardware, ISR software, and reset. That's our reset pointer. That's the first instruction we're going to execute. Yeah, and then we're going to start our general purpose RAM-ROM after that. So let's, for ease of debugging, let's go ahead and create a program here. And let's see, we'll call it test prog. And our test prog is going to be type characters. It's going to be of an indeterminate length for now, and it's going to start off with something of the sort of GATC da 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 da. We'll come back to that in a minute. That's our initial test program. Let's see, we got all that. Now let's start with the main. Void main and argc argv's. So we have some inputs later. We can maybe pass our program into the command line, since these are going to be short programs to begin with. There's our main. Let's see, do we want to say anything initially? Or do we want to just start processing? I'm going to say we just start processing. So a couple of things we need to keep track of. Got our program counter, stack pointer already. So we need to have our, well, our program counter is the location in the program here. So, and normally we would take our test program and read it in. So first off, let's initialize everything. I guess it would be helpful to have some standard IO and standard lib and memory. Include path. Oh, I don't think I've actually built this yet, so that's part of it. Let's go ahead and build and say it's that. I cannot find the include path. Really? Well, that's rather problematic. If you can't find any of the standard includes, what is that about? Why can't it find the standard includes? Oh, because I didn't call them correctly. Didn't give them the proper names. What do you not like about that? No standard IO.h. Yeah, okay, there we go. Run and done because it didn't do anything, right? All right. Oh. That is not 16 anymore, is it? 16, 17, 18, 19, 20, 21, 22. Or I can just leave it empty, right? What does it not like about that? Excess elements in array. Well, yeah, there we go. It went away once we recompiled. That doesn't need to be there. Right. Everything's lovely. We're going to go ahead and print GAT-C emulator. GAT-C emulator, and for now we're going to have the test program. So we probably are going to need we're going to first off clear everything out, right? Initialize our memory and all that kind of fun stuff. So memset memory 0 size of memory, and see what else we want to initialize. So the idea is that after all of these registers, we would start, our program would actually exist in memory, in this same memory. So we're going to copy from our test program into memory, and we can actually string copy into the address of memory and 42 and 43, so we start at 44, yes? Yeah, 44. So address of 44, byte 44, we're going to string copy our test prog into there. And then the reality is our program counter should start at the address. Oh, no. Yeah. No. Yeah. So our test program's at byte 44. So we should also initialize our regs to the reset PC regs to the reset is going to equal, or rather, the dereference of regs to reset is going to equal 44. 44 with F's. 44. And that way, we should probably have a function to print regs as well. Print regs. That'll just print out our registers for us. Let's see. So yeah, clear our memory. Set the initial register for the reset to 44, and then copy our program into memory starting at address 44. I suppose. Could I do that? Yeah. Should actually do that. Yeah, that looks right. So we're saying our address, or reset address, is going to be at 44. We're then going to copy our test program into that address. And that should have us running. So most of this function is going to be that our to the program counter is going to equal process instructions to the current value of regs to the PC. And then of course we're going to need a regs to PC, so that's not character pointer. Wait. Regs to PC is not a character pointer, it is a unsigned short. Unsigned short pointer. Same with this. Oh. Unsigned pointer. And then of course, so these are the individual underlying commands. This is going to be the main process instructions function. So we're going to process instructions. And let's see. Yeah, that should be it for this level. That's essentially what we're going to do, is print out that, and then we're going to do this until when. I guess until the PC goes to 0, because the PC should never be 0. It's always going to start at 44 or better. So we could use that as an endpoint. Yeah, I suppose. So we're going to do this loop of this one instruction, not a very big loop, while the dereference of the regs to the program counter is something other than 0. Oops. And that's pretty much our program there from this level. All right, clear memory, set the initial reset vector of 44, copy our test program into memory starting at our reset vector, and let's double check. Yeah, that's right. Pretty straightforward emulation, huh? Suppose we're probably going to want to have a tick counter, right? And then be able to tell what our GPU speed is. So unsigned int tick counter equals 0. And tick counter plus plus here. Actually, we'll do that ahead of the instruction process. And then while reg does that, maybe we print it out at the end. Program complete. The instructions processed. And that's our tick counter. We'll do something else with it. Maybe do some tick counts per second or something like that. Let's see what else we got. Looking good so far. Before we do too much more, let's go ahead and print our registers. Oops. Extra the brace down there. So create our print reg function. And GATC registers. And here's where we get to a debate I've had this whole time. Even though we're actually dealing with things in everything's binary, so we're dealing with it in hexadecimal mostly. Do I want to print it out in base 4 using GAT-C, or for now we're just going to print them in hex for convenience? So let's see. Kind of like putting the value in front of the name, but we won't. Let's see, and for verbosity purposes, we'll put out their whole names. 0 reg. And percent 08 with 8 hexadecimal. It's only 2 bytes, so 4 X, capital X. And this is going to be dereference of regs to the I suppose I could just run through them all, but for, again, verbosities, we'll use the register names. Two, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. A register. E register. C register. Let's just do this to keep it simpler, eh? Come on. So we've got Z, A, B, C, D, E, F register, and we've got input A, B, C, output A, B, C. Input A, B, input C. Output A, output B, output C, and program counter and stack pointer. PC. Why am I saying reg every time, eh? I'm printing the registers. Why do I need to say reg over and over again? And the flags. And these aren't so much registers as they are ISR locations. Let's do this real quick. Let's find space REG. Really? There's no find in selection. Ugh. Place with nothing. Find in selection. How annoying. All right. So do we need to print these? I don't think we need to print these. Since we're just printing the registers. And registers, yay. It's less help than it looks. Program counter stick footer. Ugh. Auto help. Not always an auto help. Here we go. It prints out all our registers. Expected while. Oh. Wait, that's my do while. Why did you expect while? Oh, embrace. There, that's why you expected while. All right. That's our print ridge. Extra bracket there. Everything looks good to go. GAT-C emulator. Let's call print regs. What are you complaining about now? Void. All right. That should be straightforward enough, eh? Let's see. So we start off with clear memory, set up our registers, or reset register. Although I didn't print those. Let's see. Let's see, we'll call these vectors. Well, since that's what they are. And the reset vector, let's see, do I have all these defined in here? Yeah, I have these all defined. ISR, ABC, hardware, software, and reset. That line. And interrupt A. Is that what they were? Yeah, ISR, ABC, HS. ISR, A. B. C. Hardware, software, come on. Hardware, software, reset. Right. Hardware, software. reset. Oops. ABC, hardware, software, reset. And we're probably not going to need to see the vectors over and over again, but it's convenient for debugging for now. And I hate having a non-underlined bit here. All right. Registers. So we'll do that and we'll see if we're all set up. Yeah, that looks all legit. Let's run it, see where we get. Assignment too short. X integer from pointer without cast. Assign short pointer. Oh. Yeah. So they're not going to return unsigned short pointer, they're just going to return unsigned short. And they're just going to take an unsigned short. Their inputs. Trust me, working all this out with prototypes is going to make implementing them easier. What don't you like? Unsigned short process control. Ah. Weird. Yeah, no problems. Build finished with errors. And define reference to process instructions. Not a surprise. So process instructions. Right now we're just going to return 0. And it's probably going to complain about undefined references to all of these. We're going to comment them out for now. There we go. There's all our values. Registers are all 0. Our reset is 2C. And then, all right. Registers. Let's print out the program for now. so we can see what we're trying to do. So we're going to printf program as one long string starting at the memory at the reset locations. Drags to the reset. Right, that looks correct. And it should just be GATC dot is our program for now. And of course I can't stand it. I have to have it formatted. And then up here, before we print a program, let's give it a gap there. All right, run that bad boy. Segmentation fault. That's because that's not the address of, there we go. And now we have our own, annoying. These JSON files are kind of annoying for configuration. I'd rather just have the terminal external. Let's see. Side panel. Internal. Just rather have it external. See if we create a launch JSON file. Does it automatically fill it in? No, it doesn't. Add a configuration. Ugh. I don't like any of that. Let's just close it without saving it. So apparently you have to set up a JSON file for launch and then say in JSON language that you want your terminal to be external. And that's just kind of annoying to have to set up for now. Nobody's really, well, maybe somebody's interested in it. Let me know, are you interested in looking at the launch JSON file for these things? It does help in debugging later. And I do already have one. Let's see. File. Open file. In the open yep. Not the open yep. The yep 1508 source. The emulator. Linux. No. I thought I had the JSON file in here. Annoying. It really is annoying. Yeah, whatever. I'll keep the terminal in here for now. So emulator starts, we print out our registers. Our reset vector is to C. Sure enough, it prints the program. That should be it. But of course, before we actually start running the process, right, we should make our program counter equal our reset vector. And let's do that before we print our registers. And maybe we should say what we're doing here. Clear memory net registers. Set vector to start of reset start after regs and vectors. Copy the test program. Into the memory. Then we're going to set APC to the reset vector. And that amounts to dereference of regs to the PC equals dereference of regs to the reset. Not technically a register, mind you, but in the same family. So, yeah. Says instruction. That'll be pretty straightforward. Right. From 1 instructions processed. Sorta. But actually 0. But anyway, there's our reset vector of 2C. And our program counter is already initialized to that reset vector. Everything looking nice and kosher so far. Let's see. Hi, everybody. How you doing? Let me know in the chat if you see anything that I'm going off in the weeds on. Let's see. Got everything nice and reset there. All right. So now we're actually going to start processing instructions. And to start processing instructions, we are not returning 0 anymore, but we're going to do a switch on the value, the character in memory that we're looking at. So the short input is initially our program counter. All right, here's what we set our reg PC here. And so then we pass that in, and so we're going to look at memory to the input location, and that is going to be a character, one of our GATC characters. And I probably get this wrong all the time, but case G. I guess we should worry about uppercase and lowercase, but not for now. Case G. If we are the G command, we are going to call the process go function. So with the input, and we are going to say, do we just return from here, or do we set a value? Oh, having ourselves some more streaming issues. Lovely. Open widget. Stream is healthy. Now it is errored. Wish I knew what could fix that. Dang it. Yeah, I guess that's just my machine. Although again, claiming to use all of 5% CPU, and maybe I should bump that up again, but we'll try that next time. So if we've got a capital G as our first command, we're going to process the go command. And since we know it's a go command, we should be able to make the input we increase the input by 1. Yeah, I think we're going to increase input by 1, so that when we go to look at the inside the go process go, won't have to deal with the capital G. And this is just going to let's not do that. Let's go ahead and make a return value, default it to 0. So return value equals process the go command, break the says ALU. Did I comment on them? No, I did not. Oops. There we go. Excuse me. Process ALU. break there. E. Process transfer. You don't really need the last break because it's already at the bottom here. Although we will use it because I believe there's a, is it case else? Or is it just else? I don't recall. It might be else. Actually, I guess I don't need it. Because if it's not one of those, then return value remains 0 from up here. And we return 0 and the process halts. Oh, yes. GATC. And instead of process transfer, process control. So that takes care of the first letter, the command letter. And we go off to different functions for each command letter. And I suppose the easiest is to process go, because it's the jumps. So everything other than the call is pretty straightforward. Oh, it's CTRL, not control. CTRL, there we go. All right. So that'll take care of the primary call letters, or command letters rather. And if we run through all this, well, I suppose it would help to return the return value. All right, let's see if I got all that right in the first try. No problems detected. No problems have been detected in the workspace. Okay, what about the terminal? Well, of course there's been problems. I haven't put in these functions yet. Alright, so go, ALU, transfer, and control. Those are the prototypes. These will be the function bodies. Right now they're empty function bodies. It returns 0. So that we have a function body for each one. So I think I'm trying to avoid having to make too much commentary here, right? This is pretty straightforward. We're looking at memory based off of the input value. If it's a capital G, then we process it as a go command with the input value plus 1. Same thing for A, T, and C. So this is just sort of a funnel, if you will, or an initial subdivision of functionality, just so that we can build it up as we go. I think I can also do this. case lowercase. Yeah, we'll force it all to uppercase, I guess. It's a lot cleaner looking. So process a go command. Do we want to do that first? Probably. Go commands are jumps, right? So we also want to be able to convert a register number with GATC letters into a value from 0 to 15. What's the best way of doing that simply? Yeah, I don't know. There's a number of ways of doing it, but so the first thing we're going to want to do in here, we're going to process the go command. Now we're going to switch based off of the operator, right? Do stuff for each operator. And do stuff for each operator. And the go commands. Let's just go ahead and copy this line out. Use that as our comment. Wonder why I did that. There we go. All right. That's just a reminder of what we're doing. So now we're going to switch again off of the memory at the input location. And it's going to be the same set of switches. Oops. As we did down here, or not down here, but up here. We're basically going to do this again. But for the go function, and whoops, I suppose we have to do inside short return val equals 0. And now we're looking at GATC, but as the operand. Case G. Jump if the register is passed is equal to 0. And so that's what we're about to do. And jump if the register is not equal to 0. This is jump if the register contents well, not the register contents, but yeah, the flags have C or B set. double vertical bar for or. And then this is call memory address, which in our case is going to be 8 characters long. And we just always call. So the first one is jump if the register equals 0. So that means we're going to have to take the next 2 characters after this input, convert them to a value between 0 and 15. And so then we're also going to have to convert the location. And we might as well do that. Let's do this. Our character operation is equal to this. That way we can change memory later. Then we're going to have our also character reg number, and that is going to be to convert the GATC to number, or to integer. Convert GATC to reg number. That way we know it because it's 2. So convert GATC to register, and we're going to do it at memory input ++. So our operator was the first character that we passed in. The next 2 characters are our register. So we're going to increment that. And then of course we need to create this function here. So we're going to, and the only reason I'm making it a character instead of an integer is because it only needs to be 0 to 15. So oops. And this is an unsigned short of our input location. I am getting a lot of delays this time. Don't know why. Lots of streaming delay. So return val equals 0. So by default, we're going to return the 0 register. That'll also be the case if the number is invalid. But we'll protect against that earlier on. So there's going to be a lot of switch statements in this function. Yeah. Is there a better way of doing it? GATC. I don't know that there's much of a better way of doing it than with the switch statements. I mean, They're clean, anyway. Straightforward. So, yeah. Might as well just call this the switch program. And so again, memory to the input location is going to be the first character of our register address. And if it is G, it is equal to 3. It's not actually equal to 3, is it? I mean, it's 3 in the lower. Well, it's 3 times base 4, which is 12, right? Yes. 12. I'm doing this because it's big Indian. I'm looking at the bigger number first. And we're just going to be verbose about it. So, case C, we don't have to do anything to it in the case statement. And then all these other ones, it's plus equals 12. Eight. Four. Yeah. We don't actually have to do anything for C, but maybe for verbosity reasons, we add the 0. It's a do nothing line, but anyway, makes the concept clearer, I guess. And we've done that for the first larger place value. Now we go to the next place value. We do the exact same thing, except instead of times 4, it's just 3, 2, 1, or 0. So the maximum you could have is 12 plus 3, which would be 15. That makes sense. Maybe? Mostly? Sort of? Alright. Just a switch statement machine, aren't we? So, in case anybody's wondering what the switch statement does, it basically says based off of this value, whatever this value is, and everything's a number of some sort. If that value is the equivalent of the value that is the uppercase G character, did it actually say? Oh yeah, look, it says if it's 71. So if this memory location is 71, then do this instruction, and it would actually just fall through doing all the other instructions, but you have to, that's why you have to have a break statement. So it says, okay, do that one instruction and then exit out of the switch statement altogether. So let's be a little more verbose about this. Check the upper nibble, quibit. I don't know what to call this. So let's see. Convert a number between 0 and 15, which in our language is CC to GG. Check the upper character. Character. E-R? Yeah, character. Yeah. And then check the lower character. I guess maybe I should put it in these terms. We are going to check the 4's place because we are base 4. And we're going to check the 1's place. Yeah, that's the better way of putting it. Just like in decimal, you have the 1s, the 10s, the hundreds, the thousands. In base 4, we have the 1s, the 4s, the 8s, the 16s, the 32s. I think that's right. So yeah, check the 1's place. GATC, GATC, everything's GATC. Alright, so that gives us our register. There is probably a better way to do this in a loop, because I'm going to have to do the same thing for much larger numbers and up to 8 characters. Yeah, because our destination address is 8 places long. This is good for registers anyway. I mean, we're about to do memory locations too, but in any case, return the return value from here. And yeah, and we'll do this and then we'll start single stepping. Anyway, single stepping is easier to debug. So here, we're going to have unsigned short address. So that's going to convert that. Then we're going to have to increase the input location by 1 to get past the secondary value of the register. Then we're going to be on to the addresses. So convert GATC to short, really. Memory at the input. I can do input plus plus. watch this. I can do ++ input. And I don't need this line. So, convert GAT-C to short. We're going to need that to create our address as the next set of values. Perhaps processing jump instructions weren't the most interesting. Unsigned short convert GAT-C. Convert GAT-C to reg. That should not be an unsigned short input. Well, yeah, it is. Is it? No. Yeah. Yeah, so the operator equals the memory to the input. We increase the input by 1. The register that we're looking at is going to convert from the input. Increase it by 1. Is it 1 though? It's actually by 2. I can't do that because then it'll actually do that right then. Input plus equals 2. Yeah, there we go. Yes, process go was not. Process go. Yeah, because I'm just taking the input. Not, yeah, the input is the location in memory I'm looking at. So process go. No, that's right. What is your red underscore about? Oh, because I didn't finish the function above it. That's why. Now that's better. And then here we're going to all addresses have to be the full 8 characters for the address. So we can basically, yeah, we can run backwards. We'll take this. We're going to do that to it. We're going to do this 8 times, yes? Or int I equal 8. I it's easier to count up. I less than 8. I plus the plus. Right. Equals 0. And a memory to the input is one of these letters. It is going to be plus equals 3 times 8 minus I. And we will go from the highest place down to the lowest place. Three, 2, 1, 0. And that should, I say should. Hey everybody who all's been watching. We got a few people coming and going. Staying on to bump up the average. Thanks for staying on for that. You'll notice some of these things seem a little redundant. 1 times whatever versus 0, or rather 0 times whatever. It's there for verbocity's sake. Obviously, it's not necessary, because adding 0 times anything would just be adding 0. So we're just spinning cycles for the fun of it, I guess. All right. So we're going to manage, I think, to write a program that loops to itself infinity-wise, I suppose. Now, I think that's going to convert the value correctly, because this 8 minus I basically does it backwards. And yeah, I believe that's correct. I believe that will work correctly. Again, I don't need the actual processing of the C's, the zeros. They don't add anything. But it should be clearer. So let's add some comment to this. Loop from the, what is it, the 1s, the 4s, the 8s, the 16s, the 32s, the 64s. Let's see, 1, 2, 3, 4, 5, 6, 7. That doesn't look right. That should not be the 256's place. Oh, yeah, I guess it is. Because we're going up to 65,535. So really, we're going to do this, but we're going to do it backwards. So from the 256, 128s, 64s, 32s, 16s, 8s, 4s, and 1s places. Because again, we're base 4, so the lowest value represents 0 through 3. The next value represents the number of 4s, and then after that we get 8s, 16s, and 32s. Up to 256, so we can have up to 4 of each of these all added together, which should be 65,535 as a maximum value. And yeah, it looks like that will work. And yeah, that'll work. Let's see. All right. So we get all the way through that. We come in here, we get our operator. We increase our input position. Then we convert the next two characters to our register number. We move past those two characters. Now we convert the next 8 characters to an address. After that, we don't really care what the input value is because it will have changed. And it'll especially change if one of these things goes through. If it doesn't go through, though, then our return value should be just past the instruction. So our input is going to be plus equal 8. And by default, our return value should be, just do input plus 8, skip this. So, put a little more explanation into what we're doing here. This gets the operator. That gets the, equals the next character in the instructions, our program. Then edge equals the value of the next 2 characters. And then the address equals the value of the next 8 characters. And then by default, if no jump happens, we move on to the next instruction. Yes. And that is just wherever our input was plus the 8 that characters that were converted here. So in other words, if the jump fails, we just move to the next instruction. If the jump succeeds, then we're going to return that address of the jump. And so this first condition is if the register condition is 0. So if the regs if the value contained in the register based off of the register number that we deciphered equals 0, then I'm going to actually do this all on one line. We will return the address from the jump. This is the same thing, except that it's not equal to 0. And this is where we get a little more complicated, because we have to look at the flags register. And instead of the register we've specified, because it's going to be XX, right? Let's look at the docs again. Flow control. So if we're T, we're going to jump based on if either of those two flags is set. Those two flags are the two upper flags in the 15 register. And that's going to be a little bit annoying to check, isn't it? Because the idea was each of these is each of these has a value, and they're not so much bitwise. There's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 of them. I mean, I guess it does have a bit value after all. Because in theory, these are all either going to be 0s or 1s. Well, we'll figure that one out later. Skip that one for now. Except that it's going to be based off of the flags register. If the flags register equals some number, which we have yet to figure out. C, we'll just call it C, or the dereference of the flag character equals that. Or maybe we'll end it with some flag. Like I said, we'll figure that one out later. And then same thing with the function call. Let's see, that's just a straight function call. So that's got another call the function at location address. Again, figure that one out later. For now, we're either going to jump if we're 0 or jump if we're not 0 on a given register. That's enough to give us some basic flow control. And oh, what is all this complaining about? expected a type specifier. This probably means I missed an end. Yeah, there we go. Why does that return 0? Process go command. There we go. All right. Let's do stuff for each operator. There's our operator breakdown. There's our return address scheme. Hopefully that converts to the proper address. And so we're going to have to make our program mean something. Right now it does not mean anything. If our program starts with the go function, which it does, it actually says go GATC. So go if jump is not equal to 0. Jump if the register is not equal to 0 and the register it specifies is 40. Yeah. Not 40, but register 4. And then it's going to get to this, which is an unknown character, and it should end. So let's just walk through it this time. First off, let's see if it compiles. Well, we'll see if it compiles, and we'll start at the very beginning with the breakpoint. All right, looks like it didn't complain. Set all those. We got our tick counter and so forth over here. Registers. These are the processor registers, not my registers. So print that. Print all the registers. Print that. Print the memory. Increment the tick counter. We're going to process instructions. If we look at this value, we get what? Let's step in. What did we get for input? 44. That's what we should have gotten for input, yes. All right. So that's our starting location. If we look at memory, that's a whole bunch of extra stuff. But if we look at memory to the input, memory to the input should not be 44. Oh, it doesn't do that. That's kind of annoying. Let's see. Let's add a watch. Memory to the input. We're going to be doing that a lot. That's a character. Let's convert that to a character, and there we go. It shows a capital G. There we go. All right. How was that looking on the top? Okay. So we know it's a capital G because that's what our program is. Okay, that means we're going to go into the process go command. We go into process go command. We have, we blank out the return value. Really? Input should be 44. Process go command. Let's see here, the call stack. Yeah, we should have done this the other way. We want to increment input first and then go into the call. It's going to be the same with all of these. And that's what this does. If you do the plus plus after the input, then it passes the value and then does the increment. If you do it ahead of it, it will increment the value and then do the function call. So let's stop and run again. Except instead of putting a breakpoint there, let's put a breakpoint right at the beginning of our statement. Increment the tick counter. Go into process instruction. Sure enough, we're going to process a capital G. There we go. Now we have our A. And that's going to be our operand. And then we grab the operand. And we move the input. Now we want to look at the convert. So let's jump into that. Turn value is 0. Oh, did I do it again? No, because this is the increment. So, okay. So now we should be looking at, and we are, the T, because our instruction is GATC, and we're processing in GATC. So now if we're a T, we're going to add 4 to the value. Hi, new folks. Thanks for joining. Let's see. Now we've got our return value of 4. Move on to our next input, and sure enough, that's the C. And that is plus equals 0. I guess the compiler threw that out because it was a waste of space. So we are going to return our return value, and our return value is 4, register 4. So now we have register 4, which if we look back at register 4, which is A, B, C, D, register D, it's 0. So, yeah, now we add 2 to the input. And we're going to try and convert an address that is non-existent because our program doesn't have it. Because we didn't put it in there. So let's give it an address. And this is where converting to base 2 is kind of a pain in the arse. And so the debugging is so streamlined and nice. It can be. there are certain things that it doesn't do that other debuggers do that I'm just spoiled by. Let's see, go back up to our program here. Hello, thanks for showing up, Snow Crash. I guess that's Snow Crash. Alright, so we're gonna jump if oh yeah, I figured it was based on the image. How many names do you have? 7 or 8? Alright, so if this is going to be jump, if register, way too many. Jump if register 4 is not equal to 0, although it is 0 at this point, we're going to need a destination address. And that destination address, for now, is going to be the same 44. So we'll basically loop on ourselves, I think. And we'll really test the debugger, actually, because then we'll just be looping until we change the register in the debugger, because we're not going to be changing it in our code. So we need a value of 44, but in base 4. So I actually took the time to build this for me ahead of time, which was dec to GATC, a value of 44. That converts the decimal value 44 into a base 4 number, so AGC. And since we have to have 8 characters, we're going to be a bunch of C's, so it's actually going to be 1, 2, 3, 4, 5 AGC, except in uppercase. So let's put our destination address in here. 1, 2, 3, 4, 5 AGC. So that should be, well, we'll leave the ellipses in there just to bug anybody who's younger than me. There we go. Now our program says jump if the register, don't be moving characters around. Jump if the register TC is anything other than 0, and currently it is 0. And so it actually should fail that jump and come to this next address. So let's double check that. This jump should fail because register 4 is 0. And by register 4, I mean D. Since we're all 0 base still. And yeah, and that's the extent of our program, so we don't have a whole lot of other locations we can go to. Although I guess we could jump to 45, and then we'd be processing an A command. And just jump internally to the same instructions. That would be a mess. But anyway. Alrighty. Let us roll. Rock and roll. There we go. Tick counter. Jump into process instructions. We're going to process a go instruction. The operand is an A. So we're going to convert our register. We already saw that happen. So we'll step over it this time. Process that. Now we're going to see if we manage to process this address correctly. So our Our address is, our next character is C, which is a 0. So switch on C, input plus plus. It's still C. That's 1, 2, 3, 4. You can see input changing over here. 5. Now we get to our A. And let's see, I is currently 5, so 8 minus 5 is 3. 3 times 2 is 6. So our return value goes to 6. And rank. Then we are looking for a G. At this point, I is 6. So 8 minus 6 is 2. That's another 6. Char menu. Memory input X for hex. Ah, yeah, but I'm actually looking at the character, not the X, but that's helpful, or will be helpful for sure. All right, now we're going to add another 6 to it. What was the number we were looking for? We were looking for 44. This doesn't look like it's going to work properly. But maybe I have another one-off error going here. And then C. Yeah. Well, return value was supposed to be 44. So we did go through all of them, I think. Right, yeah, okay. But our return value is 12. That is not what it is supposed to be. What, pray tell, did we do wrong? Let's go back, look to our value up here. AGC should have been, C is 0. So this should have been, this is that's what I think it is. Times 4. Because we are base 4, yes. Perhaps. Yes, more multiplying by 0. Because this is the 8 units times 4. I think that's right. So much easier to just don't give me no me. So much easier to just run it and step through the debugger than it is to sit here specified. You know, single step is so much faster. Alright, so the first 5, of course, are C, which are 0. So 1, 2, 3, 4, 5. Now we get to our A. Now that is going to be, now see, will this do this? Can I do that? Is it 8 though? That's, no, that's not 8. See, this is what I'm used to in the other debugger. It would, you could just highlight this whole value and it would say what the final calculation was. Of course, one more step and it'll put that calculation in here. So yeah, 24. So there's 24. Then the G, 48. So close. So close and so far. $48. Should be 44. Is my other program wrong? Because I went and trusted ChatGPT to produce that program. Is that 44 should break down into, well, it's got to be 1, 4, right? So this character should be not G. ChatGPT, you have screwed me again. Yeah, I don't think it did that right. It always does. Yeah, right? If you wanted to really give people extra work, you would just make your code generator screw things up. But let's see. So this is going to be 44. So in base 4, 4 is just TC, or 1, 0. In fact, let's do that in base 4. Let's do our own base 4 conversion. So the 1's column is 0. The 4's column has a 1 in it. The and that gives us 40 left. Did you do that backwards? Now let's see this. Let's just do a I don't want to bring that up. That's going to take forever. So it's 11 fours, yes? There's 44 in base 4. Number in base 44. I don't want to do a number in base 44. Decimal to base 4 converter. Huh. this convenient web-based converter. Sure enough, 234, which would be AG0 or AGC in my lettering. So it had it right, and I'm still wrong in my conversion. That's what I get for trusting ChatGPT. I got it wrong, and they got it right. Now I'm looking bad. What am I doing wrong here? Here we go. This should be the ones column, right? This is the fours column. No. That's what this is supposed to be doing for me. One, fours, eights, and 16s. That don't look right either. Just because it doesn't look right doesn't mean it isn't. One, two, three, four, five. A. That's already 48. So what am I missing here? No, not one, fours, eights. No, it isn't it. It's one, fours, 16s. Because that would be 4 to the 1 power, or 4 to the 0 power, 4 to the 1 power, 4 squared, and 4 to the 3rd power. Quick, what's 4 to the 3rd power? Stupid calculator. Decimal. Let's just do a basic one. 4 to the 3rd power. Well, 4 times 4 times 4, right? That's 4 to the 3rd power. 64. Well, that looks like it's going to be even wronger. What are we missing here? Yeah. Yeah, see. Three. Nice fives. 3, 3. What am I screwing up here? Gonna be too clever. All right. Have a good one. We'll see you tomorrow. Or you'll see me tomorrow, I guess. What is causing my conversion headache? I think it's because the 8 minus I is actually the place. And then it's the number of fours. Right. 8 minus I is the... So in the case of the 8th, 0 times 4 to the power of 8 minus I. Because in the case of it being in the case of it being 8, right? Well, it's not 8, it only goes to 7. So if we get to 7, then 8 minus 7 is 1 in all of these cases. And right. 8 minus 1 would be 1, 4 to the 1 power 1. So this needs to be 7. Because 4 to the 0th power, like everything to the 0th power, should be 1. If and I remember my mathicals correctly. Let's see. This even doesn't even have an x to the y. There we go. X to the y power. So if you do 4, 2 to 1 power, we get 4. If we do 4 to the 0 power, we get 1. Yes. So if we get to the very smallest digit, which is the one all the way over, that means because this is 0 to 8, to less than 8. So this goes from 0 to 7. So in the case of us getting to 7, then 7 minus 7 is 0. That'd be raised to the 0th power. Plus 1. Because it's 0th power, 1st power, 2nd power, 3rd power. It's weird because I'm going backwards. So in the case of I being 7, this is 0, 4 to the 0th power is 1. Oh, no, yeah. Because all 4 of these are in the lowest digit. So if we're in the lowest digit, it's raised to the power of 0, which means it's 1. It's either 0, 1, 1, 1, 2 1s, or 3 1s. Then if we are in the next digit over, so we're 7 minus 6, then we're counting the number of 4s, and we either are counting 0 4s, 1 4, 2 4, or 3 4s. Yes, yes. It all makes sense now. All right. 1, 2, 3, 4, 5. All right. So A's is going to be wait a second. How did our return value become 25 already? Return value 0. How did that become 25? I was going too fast. Definitely 0 there. Wow. Order of operations. So it's doing the multiply before it's doing the power, or vice versa. It's basically saying 0 times 4 raised to the 7 minus 5 power, I think. Because plus equals 0 times anything, it should be 0, not 7. In the first case, this is 0. Maybe I'm trying to do too much here. Maybe I should just convert this switch statement, convert it to a number from a letter, and then concern myself with yeah, let's do that. Place value equals 0. Place value equals 3. I'm going to do too much calculation at once. It's not helping me. Just do place value. All right. So now we have the place value. Now we are going to say the return value plus equal the place value Place value times the place that we're in, which is 7 minus seems like I'm doing the same thing, just in one place instead of 4. That's going to be 8. 4. Don't need parentheses, do I? So, first time through, I equals 8, because it is the 8th character position. 4 to the 8th power. This is 0. Minus 1 power. I think that might be right, and that's probably more straightforward. Because I'm going to go from 8 to 1. Yeah, from 8 to 1. Already going on 3 hours. Stuck in the math weeds. Let's see. So I'm going to go from 8 to 1. Except I'm going to be subtracting 1 as I go. And that makes sense because typically numbers are like in decimal numbers. 1, 2, 3, 4, 5, 6, 7, 8. This is 10 to the 0th power, which is 1s. Then it's 10 to the 1 power, which are 10s, and then 10 squared, 10 cubed, 3, 4, 5, 6, and 7. Yeah, that looks like it makes more sense. All right. Yeah, let's give that a shot. All right. 8 to 1. Ugh, why are you doing that? Oh, ugh. This is not the raise it to a power function in C, is it? That is exclusive or some other useful kind of calculation. Yeah, that is not doing what I think it's doing. That's why it's all messed up. I think I have to use the power function. Is it POW? Int POW. No, what is the raise to a power function in C? It's that in math. But I don't think raise a number to a power in C. Using the POW function. In the math header file. Yeah, that's why it's not working. It's supposed to be like that. Power 4 raised to that power. That's why. So the caret character in like all of regular mathematics is raised to the power of. But in C, that's exclusive OR, which is why we were still getting a value even though we were multiplying it by 0. There we go. And it doesn't know where the power function is because I didn't include the header. Include math.h. And undefined reference. Ugh. Really? You're gonna force me into doing a freaking build? Or. I don't want to go look for the math library and include it and have to link that together. I also don't want to have to calculate the powers of 4 over and over again. Lookup table, here we come. So, since we don't need to figure out the powers of a bunch of things, let us at the top of here create ourselves a lookup table. Short. It's going to be an array. PAL4 array of 8 values. It is going to consist of the powers of 4, which start off as 4 to the 0 is 1, 4 to the 1 is 4, 4 squared 16, then 64, and then bring out the calculator. All right. Click 4 raised to the 4th, 256. 4 raised to the 5th, 1024. 4 raised to the 6th, 4096. 4 raised to the 7th, which I think, yeah, is the last of it. 4 raised to the 7th power, 16,384. So what I did there was just create my own little index of values that are the powers of 4, from 4 raised to the 0th to 4 raised to the 7th. And that it should be 8 values, yes, 1, 2, 3, 4, 5, 6, 7, 8 values altogether. So now I've got my powers of 4. I don't need your flippin' math function, math library, and have to link with the math library. Don't need that. And just come down here to my function and say PAL4 to the I minus 1. There we go. Lookup tables are so much faster than calling the actual math functions anyway. And if I were going to have to do it for more than 8 values, maybe it would be worth doing. Or if I had to do it for other than powers of 4. But that not being the case, I can just do the lookup table. All right. That is not what I meant to do there. Meant to do that here. All right, now we run off. Our place value is 0. Times any value from the lookup table is 0. Yes, that's good. 2, 3, 4, 5. Now we get a place value of 2. Place value of 2. Our lookup table is the 2. That gives us our 32. Now we're looking for a place value of 3, but we're already down to that. So that's going to give us the number of 4s. That gives us a 44. Looking good so far. Now we get a place value of 0. Place value of 0 times anything is nothing. There we go. That's how we solve that problem. Return to your basic math. place value times the power of your base to the location, or the place number minus 1. There we go. So now we've got our address. We return our 44 address. We increase to the, we default our next address. Then we're going to say if reg to the reg is not equal to 0, except reg to the reg is equal to 0, so we should just break out of this. Yep. And we return the return value, which is the next location. Almost. The next location. 56 is the return value. That can't be right. 56 can't be the return value. Our program ain't that big. How did we get a return value that big? All right, that's converting the number. We did this already and it converted properly. So let's step out of that function. Yeah. Our input, where's our input value right now? It's 48. Oh, must be getting too late for me. Our program is not that big, but it doesn't start until address 44. So yes, address 56 is an appropriate address because we skip over that 8 value. So those 8 bytes, right? So +4 plus those 8. Return value is 56. That's what we return from. Our return value is 56. Right, our return value is 56. So we're going to Go in and process instructions again, which gives us our 0, and then we're out. All right, let's do that one more time. Skip out of that. Return address is 56. We don't take the jump. We return 56. Return 56 there. We now go into process instruction again. And memory to the input is a dot. And because memory to the input is a dot, which is an unrecognized character, we consider it the end of the program. And we exit. Having done 2 instructions. Two instructions done. I guess I could dump the registers at the end here too, so that we see what the registers were when we initialized and see what the registers were when we exit. And let's see. Yeah, print regs. And we will do that at the end of our main loop. All right. So what that should show is that the program counter is at 56 at the end of our 56 decimal, which I'm printing everything in hexadecimal, you know, because just cuts. All right. This set our PC to 0. That's the whole reason why we ended the loop, is because the PC was set to 0. Well, the next thing I want to do is probably do a transfer instruction so that there is something in register 4 other than nothing. And so our program will consist of maybe not transfer. We can do an ALU instruction, and the ALU instruction will subtract 1 from the register that's already 0, and that will make it the other end of the value, which will be 65,535, and that'll be something other than 0. But we will do that next time, as this is drug on long enough, and it is getting late in the day, and I've got work tomorrow. So thanks to all who stopped by, however briefly you may have stopped by, and we will catch you all next time, and hopefully we'll have advanced a little bit more, and we'll go from there. Thanks everyone for joining. We'll see you next time.